Welcome back. Today, we're diving into the invisible architecture that keeps our entire world running. We're talking about the unseen blueprint for electricity itself, the load flows study.
You know, it's easy to take for granted. All the data centers, the factories, the buildings we live and work in, they all depend on a perfectly steady, constant flow of electricity. But that stability, it doesn't happen by accident. It's the result of some seriously meticulous, invisible design work.
And that right there is the million-dollar question for engineers, isn't it? How do you build a massive electrical system and know for sure that it will handle anything you throw at it? How do you predict failures before they happen, especially when the system hasn't even been built yet? Well, the answer is pretty cool. You build a perfect virtual copy of the entire power system first. A digital twin, where you can safely simulate disasters, push every single component to its breaking point, and find all the weaknesses, all before a single real-world wire is ever laid.
Okay, so let's get into it. To really get why this digital twin is so critical, you first have to appreciate just how much of a balancing act a real power grid is.
Probably the best way to think about an electrical grid is to imagine it's a city's water system. You've got your generators, which are like the reservoirs. They push power, the water, through a network of wires, which are the pipes. And the voltage? That's just like water pressure. If it's too low, you get a trickle. If it's too high, well, things start to burst.
And just like that water system, the grid is always facing challenges. Engineers are constantly working to keep that voltage, that pressure, perfectly stable everywhere. They have to stop components from overloading. That's literally a pipe bursting. They also have to manage two kinds of power. There's real power, which is the water that comes out of your tap, and then there's something called reactive power. Think of that as the water just sloshing back and forth in the pipes to keep the pressure up. You need it, but it takes up space. And of course, you always have to plan for what happens if a main pipe fails.
So, how on earth do you manage all that complexity? Well, that brings us right back to the engineer's secret weapon, the digital twin.
Now, in the world of engineering, this digital twin has an official name. It's called a load flow study. The IEEE standard defines it as a simulation that predicts exactly how power is going to behave all across the network. It tells you the exact voltage at every connection point and how much current is flowing through every single wire.
And here's why that is so important. And I'm quoting directly from the standard here. A load flow study lets engineers test for things you would never do in the real world because it would be, quote, unwise to expose the actual physical system to conditions that are potentially damaging. It's the ultimate sandbox for designing for the absolute worst-case scenario in a totally safe way.
All right, so we know what it is and why we need it, but how is one of these digital twins actually built? Well, it's not magic, but it is a really meticulous process.
Yeah, really, how do they get from a blank computer screen to a living, breathing model of a whole power grid?
It pretty much boils down to 4 key steps. First, you map out the entire system, showing how everything is connected. Next, you plug in the detailed specs for every single piece of equipment. Every transformer's impedance, which is basically its resistance to alternating current, every cable's rating, everything. Third, you have to define all the loads. That's how much power every motor, every light, and every server is going to pull from the system. And finally, you define your power sources, whether it's the main utility grid or your own on-site generators.
Okay, so once the model is built, this is where the real fun starts. This is where engineers get to ask all of those tough what-if questions.
And this is where the study really shows its value. It's not just a static map, you know? It's a dynamic sandbox where you can just push and prod and stress test the grid's resilience.
So you ask a classic question. What happens on the hottest day of the year when every single AC unit in the building is cranked to max and the factory floor is running at full tilt? Can the system actually handle it? And boom, the simulation gives you the answer. This table is showing some major problems found in the model. Just look at that transformer, TR1. It's overloaded by more than 50%. And that cable, C9, is way over its limit too. That's our water pipe analogy again. That pipe is about to burst. These are the exact kinds of disasters you find and fix in the virtual world to prevent fires and blackouts in the real one.
So that's one test. But here's the other critical one. Things fail, right? So what happens when a key piece of equipment suddenly goes offline, either for maintenance or because it just broke? Does everything else go down with it?
Well, this is what's known as a post-contingency analysis. The study simulates that failure and then shows you exactly where the power tries to go instead. And this is where you uncover these fascinating non-obvious problems. All of a sudden, a cable on a totally different part of the grid, one that was barely being used before, is now pushed past its breaking point. It's these hidden connections that the simulation reveals, which is how you stop one small failure from turning into a massive cascade.
So let's bring it all home. When you put it all together, what's the ultimate value of all this incredibly detailed digital foresight?
Well, this slide really says it all, doesn't it? Without a study, you're basically flying blind. You're guessing. You're risking blackouts, damaged equipment, and higher costs. But with the study, you get a system that's engineered from the ground up to be reliable, safe, stable, and efficient.
And just how precise are we talking? Well, one of the key goals is to keep the voltage within this incredibly tight window, plus or minus 5%. That's like making sure the water pressure is perfect across the entire city, not just near the reservoir. And that precision is what protects all our sensitive electronics and keeps things running just right. So, at the end of the day, a load flow study is so much more than a bunch of complex calculations. It really is the foundational blueprint that makes sure our modern world is not just powerful, but also safe, efficient, and unbelievably resilient. And that kind of leaves us with one final thought to chew on. Our electrical grid is changing faster than ever, right? We're adding more renewables like wind and solar, more massive data centers, and millions of electric vehicles. So the big question is, how will these essential digital blueprints need to change to keep up and guarantee the lights stay on in the even more complex energy future of tomorrow?